Thank you.
So I was a month ago. I released this cat preprint where I announced that I did about 100 protocols in Lean, and this started out as so I've been working with the Crispin team on doing proofs in proof in a computational model, and then we had a backend for in Rock, but then Crispin decided, well, we want to use Lean, so I thought, well, I had been translating from Lean to Rock, MiniFF, and then some other things. So I thought, let's try if I can do it the other way. So I started out with we have our SS proof. That's package-based probabilistic proofs. We have so it's inspired by both the Dijkstra monads that you might know from FSR and then from EasyCrypt and CertiCrypt. But it also combines the package, the state separating proof, so that's the SSP. So this was introduced by Cedric, which I saw there, and his friends when they were working on TLS. I guess most people know that history. Kartik also presented some of that yesterday. So that's the amazing Everest project, which made a lot of progress on verifying TLS. So this is the state separating proofs. So this is what I exported to Lean. But then once everything worked with the use of LLMs, we could actually speed up and do a lot of protocols in this setting. So what we have is the subprobability model from the EMF in Maastricht, and then on top of this, we do the state transformation monad. So there's the stateful probabilistic computations, and then we have a UC variant. I'll come back to this. But most of the cryptographic protocol analysis is just by the usual game hopping that you used to from EasyCrypt. Or from SS Proof. So that's how we started. And meanwhile, I ordered most of EasyCrypt to Lean. And this is because, well, once you build up SS Proof and Lean, you have the basic infrastructure. You have all the you have the you can use this as the training data for doing new protocols. So I ported most of the EasyCrypt protocols also to SS Proof, and by now I have a lot more also that work in there. What you can also do is port the all the tactics that we have from SS Proof, and that's what I've done. But I have a few tactics more, and also ported all the tactics from EasyCrypt. So by now the proofs in Hacspec are actually about half the size of the ones in EasyCrypt. So this is one of the insights. So what was so EasyCrypt started as CertiCrypt, so a tool in Rock, but then they built a standalone tool because Rock was just too awkward to work with. Whether that's still entirely true, we don't know. We still see that SS Proof, the proofs are about 2 times longer than in EasyCrypt. In part, it's because we haven't ported all the automation. One thing that people thought was missing, what EasyCrypt is using a lot, is SMT solvers. We thought, or there was a conjecture that these were needed. It turns out that you can do everything in Rock. It's just the proofs are somewhat longer. But if you do them in Lean, it turns out that the automation is just more helpful, and the proofs actually half as long as what you have in EasyCrypt. One of the differences is that the proofs in Lean they don't record all the intermediate games. So if you write the proofs in EasyCrypt, you actually need to copy a lot of the intermediate games, and not that explicit with all the games. So that's one of the reasons the proofs are actually short. One of the main ideas from the SSP methodology is that you have code blocks, and you can you have code blocks that share their state, and this is from the SSP, the state separating groups. So you can compose them in two ways. You either compose them, you put one code block under another, or you have function calls, and that's the composition in the other direction. And I hear you also started to use this methodology. There's a whole textbook, The Joy of Cryptography, that's also following this style. So this is really getting popular among developers. And huge proofs. This came out from the verification of TLS. That's also how we use it with our with Karthik, and I'll come back to that in a minute. But what was already hinted at was that there are some categorical IDs behind it. That's already something that you mentioned in your paper. I actually made that precise now. So one thing we did in SS proof was SSP without the proof. This was just a language, but without a precise semantics. So what we did in SS proof was actually connect this up to the standard semantics for probabilistic stateful computation. So this one. So that was already there in the SS proof work. SS proof is a big library that contains lots of protocols. But now in CADCAP, we also have the games directly as lean functions, and we have more automation that also is very similar to SS-proof. What we also have is so these protocols are all checked by RFC tests. So one of the main problems that we have is the specification problem, the intent problem, especially for and this has come up already a number of times. Small diversion. I know that the people here from the Beneficial AI Foundation, they've been looking at the variable, which contains the benchmarks like Clever and Marina. The Clever benchmark, I hope I got the name right. It contains, as one of the problems, it contains the specification problem, and there we saw that about half of the specifications that they actually wrote by hand were, let's say, questionable, or there were other interpretations possible. So actually, even for humans, it's very hard to write a correct specification. So we want to do everything we can to make sure that our definitions are correct. And the great thing with cryptography is that we have these RFCs, which are very detailed, so we can directly check whether our implementation fits the RFC. The RFCs also come with test vectors. So what we did was to have the test vectors in Lee. We also have them in Rust, and we checked that both actually correspond. So I'll come back to this. We use the hex tool, which is being integrated into or connected to Anias also, and I really hope that we also can link up with talking to both Karthik and Son and Jonathan about this, that we can connect CADCrypt in precisely the same way as we did for hex. So we have the hex pipeline, so then from Rust we extract to Lean. And we already hexed when we already had a number of backends. So we had a star backend, a rock backend, SS-proof backend, and now also the lean backend. Another thing is that we used we used Lean's type class system, which works very well. And this is one of the things that actually works a bit more efficiently than the one in rock. What I did, I don't think I have it on my slide. So the hex pipeline is very nice. So it takes it started from Hacspec, which is the high assurance cryptographic software specification language, and that translated a small subset of Rust to HASR, and the idea was also EasyCrypt. This now grew out of a much bigger system with the motivation that we presented yesterday to do more and more of Rust. The initial part, so it starts from the typed higher intermediate language of Rust, and then it does quite a number of transformations. In the end, you end up with a simple stateful program, but then you can translate it to a functional program. What I did was take, I mean, that's all written in camel, but what I did was to take maybe the last third of the pipeline, embed it into Lean, because it was written in camel, so lifting camel to Lean, and then actually verified it. So there was, I mean, this is completely standard, so there's no creativity in there. But what I think would be very exciting is to actually do that for full Hex and full NES, because I mean there's this very nice description already of how NES works. I mean it's implemented in camel, so that, I mean you have a proof that it's correct. The only thing is we need to verify that. So I'm hoping that it's possible. I only did the easy part, so that there's still the hard part to be done. But I'm hoping that this is a prototype, that this is actually maybe feasible, because this is one of the critiques we often get. So we claim to have I mean, Derek already mentioned our last shot paper yesterday. One of the critiques we got there, we went from Hacspec to all the way to Jasmine, but the initial part there was still unverified because we used Hex. So now we actually have verified some parts of that. Then we worked with Kartik and with Crispin in general on Kartik already explained this yesterday. So this is well, in Quality we called it Bertie with. Do you want to let people in on the button where the name comes from?
I don't know. I like Bertie Wooster, and the T1IE is actually written T13.
Yes. Yeah. So yeah, I could do it. But what we did there was we extracted the protocols from Rust to both Rust directly, to FStar, to program, and to access proof. And then what we did there was to model the cryptographic primitives, the ones that you don't actually reason about because you assume them to be to have certain properties. You assume something to be pseudo-random. There's a type of you assume them to be pseudo-random, for example. So the only thing that matters is the types of these primitive operations, but not their actual content, because that's not the reason. Yeah.
Do you do complete security defense with complete code?
Yeah. So it's concrete as in
when if I call AES on my Rust crate,
yeah,
the axiom I get in Lean about AES being secure, does it have a number 2 to the 128?
I do both. So for the game hopping proofs, so you don't, I mean, you don't need that. You don't need what these primitives look like. But yeah, one of the things I did was actually for yeah. So let's go back. So with Hex, you translate a lot of so there's already a lot of work in verifying these things in FStar. Verifying, I mean, the cryptographic primitives, verifying some basic panic cleaners. I also ported that to Lean. What you might think is that that's hard to do because Lean doesn't have an SMT solve built in. I found one case, I think it was SHA-256, that was really hard to do without SMT, but most of it just goes through without VPCT side. So you can do that very quickly.
And the question is about the security assumptions, about the proof strategy.
The security assumptions here, I mean, are the standard ones. So
but you don't have concrete bounds, right? You're not reasoning with epsilon values.
Yes. Yeah, no, it's all with epsilon. It's very similar to what you
do.
do.
You have a concrete expression of epsilon as in terms of size.
So SSQ does do that?
Yeah, it's the same as for. Well, it's similar to EasyCrypt and SS Proof and. So it's that model we're following. Yeah. So it's sometimes called constructive cryptography. So it's in the computational model.
Yes,
Like
like
as
this
in-
model, you can say there exists a small epsilon, and that's essentially.
Yeah.
But you also compute the complete bound, and for that you need to do some, or it's computational modeling, you can do that certain step. Where you say this is exactly this epsilon plus that epsilon.
They're on the next slide.
Okay.
Yeah. Thanks. So the so here the primitives and then the protocol logic comes directly from the Rust implementation, and that's what we did here for TLS. So we know the end. So the Berkeley implementation is something that Kartik wrote himself, inspired by Russell. It was at Rust TLS. Is that correct?
By many prior.
By many. Yeah. So what we do, just to go back to the paper that we had there, and I should have added the citation. So what we did there was we verified the Berkeley implementation of TLS, and we verified it both in the computational model, in the symbolic model, and then we verified benefitness. And then we're following a similar methodology here. Yeah, so the security groups actually reason about the real implementation. I should say here that the real implementation is limited by what Hex allows us to express, and this is something where it would be interesting to do more work. So if you and this is why it's exciting that we'll now be able to combine Aeneas with Hex, then we can actually take the full implementation and not just the toy implementation. What I've been, well, it will be on the next slide, but I'll run a bit ahead of myself. So what I've been doing is you take the production implementation, you create a Hex-valid implementation that's usually just replacing some, just making changes in some key places. So for the Berkeley implementation of TLS, what we had there was most of it was directly accepted by Hex. That's the way the Hex language was designed, so that it could do these things. But the cryptographic primitives, they came from the elliptic library. So that's something that we Crispin had developed, and where we added some of our elliptic curve libraries. So I'll get to that in a minute. But the important thing is that we reason about the real implementation, not something that we wrote by hand in Lean or Rockcrest. And then we do game hopping to actually get the protocol context.
Can you explain step 3 again? What do you mean by opaque spec?
We replaced, say, SHA-256 by just an opaque constant. So the only thing we keep is the types, but not the actual implementation. So we can also reason about, and that's actually one of the things we did, reason about the actual implementation. But for the security groups, the first step you do is you assume that this is sort of problem. So
that's step 2, right? Step 2 is when you assume that the SHA-256 or AES,
yeah.
So the extracted code in step 3 is the code of the protocol itself.
No, that might be a typo here.
Okay.
Yeah. Some of these files are AI generated because I was hacking into Variate. I wanted to do more stuff, and I think I could have spent more time on that.
Quick question on the follow-up of that. This is sort of a bit of an aside, but I'm just curious. Do you know what model they used for SHA-256? Like, what was the computational assumption?
the computational assumption.
Were they modeling it as random oracle? Like what was the black box that they were using to do the security proof for the SHA in particular?
Yeah, random oracle. Yeah.
Question.
Regarding like the opaque optimization, like what do you mean by opaque? Is it like the opaque subordinate?
Yeah.
And so how do you handle like replacing actual function with an opaque one? Does it not prove anything about the evolution you've been done? Like how what's the link? What does it mean to replace like what
So I mean that's one of the things you can do with Hex. You can say, well, you extract, I mean, the full code where you can give for certain functions. You can just say how to interpret it.
okay, so you have two expressions, and for the hash function, let's say
You just have the type.
okay.
You just get an opaque function with this type. So the only guarantee you have is that you have a function of the correct type.
Okay, fine.
Yeah. And then separately, you would reason about this function. And then you would prove things like panic-freeness and so on. So now, yeah, I mean, we've been working with Kristen for a long time, and so one of the things that, I mean, the signal is one of their standard examples. So there were Rust crates for many of these. These I think I generated myself, but what I've been doing is what I said in the beginning. So because Hex doesn't support all of Rust, what you want to do is actually make a model, and that's also what we did for TLS. But unfortunately, for most of these, you actually have test vectors. So what you do is, well, the first thing is, I mean, there's just a methodology. You see a number of highly optimized Rust constructions, and those you know how to replace by something in Hex, just some slow variants of that. So you check that they still both satisfy the same test vectors. What I did was there's a Kani model checker, which allows you to prove to model check that the two implementations do the same thing. So I did some of that, and then did some property-based testing to show that the two are equivalent. So none of this is guaranteed, but this is as good as you can if you cannot reason about this code. So what we would like to do in the end is use an ES to embed both of these and prove that they're actually equivalent. But that's the part that's still bonus. Yeah, so and then we have these traits, and for these traits we actually have implementations by, so we have the abstract fields here, of which we have axioms, and then we have the implementations. And this is, so the direction is actually reversed from what we did in the last JAR paper. So in the last JAR paper, we took Hacspec, we translated it to as proof, and then we connected it up with the formally verified Jasmine compiler to actually show that ES is correctly implemented. So, and what we try to push is that the RFCs, so currently they just text, but we want them to come with reference implementation, and that's so Hacspec and Hex were our proposal to do that. So we believe that every RFC should now come with such a reference implementation. But yeah, so this is as far as we can do now. So what we did here and what we've also done in our work on elliptic curve implementations is you start from Hacspec, embed into ROC, what we did then, use and the work by Anders and others via crypto and bedrock to actually compile to an efficient implementation. The same way you can do this using Jasmine to actually get an efficient implementation. So then we would start from the Hacspec implementation and then generate efficient code. Yeah.
Just a question. So, just a high level thing. These three crates here, they are not the original signal crates.
No.
But they were written using the specs that Signal publishes.
Yeah. So they were written by a combination of things. They were we used the specs. We also just said, well, here's the Rust implementation. Here's what I created a set of skills for hex. There's also the tree setter syntax, so I can actually check very fast whether something is valid hex. So I asked it just write an implementation of in Rust that's equivalent to this Rust implementation. It should be as close as possible. So you just replace some of the difficult constructions. So
this is an independent, let's say, interoperable implementations of those specs published by Signal.
Yes.
And have been tested against the Signal test vectors.
Yeah.
And for those implementations, you're going to verify security and correctness using the PERT methodology.
Yes.
Okay.
Yeah. And what I would like to do in the end is prove that those are equivalent to the actual implementations. I mean, if once NES is strong enough and there's been a lot of progress, and I mean, we have a faster implementation of these kind of things. So a lot of people are working on that. So that would be very interesting. So because all of this is outside proof systems, what I did was test vectors, property-based testing, and so on, Bowden normalization, because that's what one does. The other thing which I haven't done is hopefully one of the Signal experts or you might want to look at these and tell me that, well, this actually looks reasonable. Once I find it, I will also go through them myself very, very carefully. But yeah, they're created from the official Signal reference. Then I just wanted to show a bit of fun category theory. So we have these packages, and this is actually fairly general. And this was, I mean, anyone that has a categorical background and sees that in these packages there's this exchange rule. You can either do vertical and horizontal composition, and it doesn't matter which order you do this. So anyone with a categorical background thinks, well, this looks like symmetric monodal categories, and that's what we actually proved. And we did that in a very general setting. So this worked for the monad of the class D category for states and probability, but this is actually more general. So there's a general class of monads and monads and forms where you actually have this structure. To some extent, I'm just being pedantic here. To another extent, I'm not, because well, we all know the ring tactic and similar tactics in Rock and in Lean. In Lean, so one of the nice things about symmetric monodal categories is that there's the coherence theorem for that. So every diagram commutes. There's even a Lean tactic that does this. So that actually gives you the proof. So it looks at a symmetric monodal category. It basically extracts the syntax, does a normalization, and then goes back. So it's precisely the same idea as what you do for the ring tactic. This now also works here, so we can use this tactic for symmetric monodal categories for packages.
But do you use just the symmetric monodal, or these looks like polynomial functors?
So we have more structure. I haven't connected it. Yeah, you should tell me more about the polynomial functors.
So we have the polynomial functors in these. Yeah.
I haven't looked at that yet. So that will be exciting to look at. Yeah. Yeah. So I've been thinking about the let's see. I've been thinking about the classic categories here, where we have this structure, because it's very close to what we were as a true. And this actually generalizes. So yeah, I need this structure more generally. the technique here, and actually there's a bit more categorical structure. So it extends a bit. So it's also a copy and discard category, and there's some more categorical structure here. So if that also, yeah, I don't know how it corresponds to what you do for it. I mean, the part of the technique is general for categorical structures, but the main thing is just the coherence theorem that we have here. And yeah, if there's a similar coherence theorem for the polynomial functors, then this will also work. Yeah.
A question about the partial composition thing. So when you write P compose Q, does it mean that Q's export are a subset of P's imports?
Yeah.
And then in the interchange law, then on the right hand side, when you do P1 compose Q1, it seems to require that the exports of Q are a subset of exports of imports of Q1, but on the left hand side, it seems that Q1 could like plug into the imports of P2, so that you have leakage between that Q1 exports can use both P1 and P2, whereas on the right hand side it's not possible.
It's a bit too long for me to parse at the moment, but
the equation holds if both sides are altered.
Is it?
Yeah.
Okay, there might be Q1 and Q2 for which the left-hand side isn't voltaic, in which case the equation dilemma doesn't apply.
If
you voltaic dilemma, then it's true.
So these are the standard rules for symmetric monodics. So if there's anything off, so the correct thing is the symmetric monodic. And the great thing, of course, is one of the big issues, as I said, is the specification problem. This all depends on mass-lib, so we know that all these definitions are actually correct. So that's why I have a lot of confidence in this. And then we can use this exchange rule in game hopping. And yeah, a number of things are actually easier if it doesn't use state. So we have a submodel of the SP comp, which is the pure ones, which is the PMF, the classic category of PMF. And then we can actually we get extra exchange rules, and then we have, so this is the statistical distance. So this is connected to having an adversary that can actually having a distinguisher that can actually distinguish these variables. And then the nice thing is, if you look at and I have them on the next slide, the game hopping steps in the X3DH protocol and the double wedges protocol, they actually have this state. So there's a lot of so one part is proving that these protocols are pure, so you don't share the states, and then you have the extra rules you can actually apply. And then the reasoning is simple. And there's a package normalization technique that actually finds the common subgroups and then does the normalization. So what we do here is we have the 5 hybrid games. So these are game hops, and so basically what you get is so this is the standard reasoning you get in EasyScript or as proof. So each time you replace one subgame by another, so you have a sequence of inequalities, and so you replace something by a random value. So this is the value. So we have the general parameter W for words. So that's cryptographic words. and then we sample uniformly from that, and then we replace them one step by the same, one step at a time. And this looks, I mean, very simple in Lean because you just do these inequalities. This is just a standard inequality region that's we're all used to in Lean. Yeah, so this is the outline for the XPDH protocol, and this is the hybrid. These are these hybrid games. This is already introduced in the paper by Cedric and others, where they explained it. There's a recent paper by Carsten Schulman and the student Marcus, where they actually do this in S-Proof, and we can do the same thing in Lean. So that's the reasoning I have used. Yeah, that's what I just showed you. I replaced a different element by a uniform sample. Yeah, I think the yeah, this is basically what I told you already. And this is a bit small, but you can just see the steps here. So this actually looks, and here are the concrete epsilons you asked about.
This is for some high-level protocol, right?
This is for the high-level protocol. Yeah. So you don't have the actual numbers, but you can also compute them separately.
These are the distinguishing probabilities. What about the running time?
The running time. The running time is not a factor here.
Surely with enough computational power, you're distinguish better.
Yeah. So that's a very good question. So the modeling here is the same as standard in EasyCrypt. So you do concrete security, concrete cryptography. So you get concrete bounds, and you show that all the constructions are actually efficient, but just by looking at them. So that's not a direct. I mean, that's not an argument that's formalized. There is a layer on top of EasyCrypt that actually does this complexity reasoning explicitly on top of that. I have something similar in Hacspec that I would like to, which is abstract enough to connect to the definitions that are now being made in CSLib, and I want to line that up, but I haven't done that yet.
I understand that it's often easy to tell the reduction is efficient.
Yeah.
That is not my case. And it's interesting if there is an axiom saying that AES is secure.
Yeah.
In that axiom, you should quantify over computationally limited adversaries. And to say that against those adversaries, the success probability is small.
Yeah.
If the running time is missing from there, what does it actually say?
But I mean those things don't show up in EasyCrypt either.
I know.
Yeah. But that's precisely the separation of concern. So I think it's a good a good observation, but typically this is split in two parts. So first you make a concrete reduction, and then later on you argue that reduction is efficient.
So is the axiom you had for AES trivially true, or is it false? It is not precise. Which way does it err?
So what is the specific imprecision that you're worried about in this case?
This statement does not include specification of adversary running time. It's only about adversary success probability. Good thing to factor the running time reasoning and success probability reasoning into separate reasoning. I'm very much in agreement with us here. But the statement as written has some meaning according to the semantics of Lee. And in the case of this protocol, it is less clearly what it should be. In the case of AES, it seems we should.
Well, isn't this for any computationally secure system as opposed to information theoretically secure? Wouldn't the success probability under an unbound adversary always be 100%?
That is my concern.
So right, so okay, so
So what you could add here is a quantifier saying that this adversary needs to be computationally bounded.
There's an implicit for all or existential over a particular adversary.
Yeah. No. So this is the usual formulation.
Right.
When formalizing.
This theorem does not say for all adversaries. This says this is parameterized by an adversary.
Yeah. Well, which means that it's for all.
This is a limitation protocol.
Yeah.
I see. Well, so doesn't that wait? Yeah. Then how does that ever go through? Like, because I take right. Like, if it's as you said, if it's computational.
If AES is specified in the same manner that for all adversaries, the probability against AES is small. And for the adversary that does 2 to the 122 steps, this theorem sounds like it's false. The axiom sounds like it's false.
So here the problem is that the epsilons are fixed values, I guess. No?
The variables.
Because usually it's like for all adversary, I can make another adversary that's used the one that breaks the protocol to break AES. So it's like if you use a lot of computations to break my protocol, then my relation will use a lot of computations to break AES, but if my adversary for my protocol is efficient, then my breaking of AES will be efficient too. And here it doesn't seem to appear this way.
So I think that the KI adversary definition would need some kind of model of computational complexity, right? I think that's somehow, well, that we want to express in some way that this adversary solves the problem in polynomial time, but there is currently no means to, like, we don't have a model of computational complexity in Lean at the moment, and that's kind of a problem, but it's a separate problem, and I think we can solve it in the future. And it would be like a compositional change in the sense that this proof, while it currently, with the given definition of KI adversary, may prove a trivially true statement, I believe that if we do the necessary like computational complexity theory stuff, and then tweak the definition of KI adversary, then this proof pretty much still holds, is I think.
So my concern isn't about the theorem on the screen. Yeah, like this one, I can see what I want to do about. But somewhere there has to be, the turtles have to stop. There needs to be a ground assumption that are using bootstrap. And I am using AES as a standing for what that assumption is. AES is not an asymptotic. There is no AES 20,000, there is only AES 128 and AES 256. Even if we're reading about computational complexity in an asymptotic sense, that is O1. With ground and 28 is O1. So asymptotic is not going to. You might say that's just parameterizing the theorem statement that all would work, but that would be a more inventive basic. It's silly. Their photographers are arguing around.
So here on the GDH as bounds and TDH bounds for lines 3 and 4, what is in the, like you omitted some part of the hypothesis, like in the reserve the 3 dots.
Yep.
And I feel like what is inside these 3 dots is actually super important and might resolve this conversation. Like what is inside?
We can look at that.
Yeah, okay. I feel like this would be the answer to this question. Like if inside the 3 dots you talk about the advantage of an adversary that you completed with A, like the adversary of the protocol, then I think it might resolve the conversation, but
there's always for the theorem of screen for AES.
Well, maybe not for AES. That implies that this adversary A cannot solve AES because it's bounded by its epsilon, and it excludes the one that you described. If this assumption that we're looking at an adversary who has a low probability of cracking the foundation, the basics, then you may have involved there. Does it make sense?
So I'm imagining somewhere in the library is an axiom, unproven theorem about A's that is roughly of this technical. It says for all adversaries, adversaries allowed, success probability is less than 2.
So if that's the case, then the formula, but maybe it may just be an assumption that we're talking about an adversary who has a low probability of guessing yes, and this is an assumption that feeds into here. So you never talk about the adversary that can do it because there's so much competition. But I guess
let's take this later on. So that I didn't try to do any innovation of the easy script proof of security of AES. So this should be similar to what the modeling in EasyScript and in SSProof and similar systems. But it's a very good question that we should find an answer to. I just don't know the answer now. And then, so what this protocol gives us is a shared session key, and then we use the double rigid to get both. So we get a keychain or two keychains to raise it. So the message key is derived from the current key by the DRG, and then we delete the old keys we get for secrecy, and then we also have the different element coming in here. We use this epoch structure, which we model later on by iTrees in Lean. So and there's a nice library, and there are actually two libraries, and I would like to have a better look at how these things are developed. So I think that this is a part that's very well developed in Rock, and there's I couldn't find I used one of the libraries, but that's something I would like to better understand also, because there's a lot more theory behind this. But the epochs actually more they actually fit quite well on the libraries. And what I've been doing is looking at the standard papers on the signal protocol and try to formalize those in the gateway system. Yeah.
What's the compromise one? How do the keys are compromised there? I mean, how do you specify that even? I don't know SSO works or anything else. So you have to provide compromise protocols to reveal keys or something.
Yeah.
And all these keys can be revealed at different times.
Yeah. And that's actually, I try to do I'll get to that. And so that's a more complex story that I try to work out more in detail. But that's precisely where these the IQs come in, because then you have a correction of that. And so I'll get to that in the next slide. So I try to do this in this you see where you have the precise models. So we get a trace of the list of epochs here. So I did most of the protocol. What I didn't tweak yet is out-order messages and some async channel attacks. So this part still needs to be done. So the signal protocol is quite complex. So we did some similar protocols with communication, like multi-body communication protocols before. But yeah, the messaging here is somewhat more complex. And I don't have a full story, but that's one idea. And the proof is by induction. And then we have the double rated, and then we have the triple rated, which is a protocol that was analyzed. Kati help me out here. Who did the analysis here? Was it were you involved in that?
No, we were more than this. If you are,
Yeah.
cryptographic is yet to do,
Yeah.
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 Should we change?
Yeah. So what you do here is you have the different keys, and then you XOR them with the post one keys. So what you want is to make sure that if one of them breaks, then you're still safe. And then you need to be clever on how to do this together with a low to actually make sure that this is still. Yeah, this is more about the protocol. So now what we have is that the signal protocol actually is a composition of those two protocols, and then there's always a question of, well, if you prove the separate ones to be secure, do you also have that the composition is secure? So that's why we use this universal composability framework. This is a framework. It's equivalent to reduced compilation, and actually prove that in Lean. And what you want to do is actually show that. That's the next slide.
Prove the equivalence between UC and game-based theorems?
No, game-based implies UC. And then where is it? There's I included the ideal functionalities. I think in some way I have the not the latest version of the slides. In any case, so there's a paper by Canetti and then a later paper by Doris and others that actually formulates signal as in the UC security framework. They provide precise ideal functionalities. So an ideal functionality is something that actually replaces cryptographic construction, and there's no way to distinguish the two. And we proved this actually, I mean, we have a UC framework in Lean, and then we proved that it actually satisfies those.
You have UC in Lean?
Yeah. Yeah. So then there's a categorical story behind it, and trying to write it up.
The comment in adding UC to VCV, like, this yesterday.
Yeah,
Yes.
No, I've had this for a while.
This is on the consensus group.
This is on the list. Yeah.
And can you say a bit more about like the game-based implies UC and formalizing that?
So that's the standard result. So if you have a game hopping,
But I mean, in terms of formalizing it in S3 or the Lean model.
so so let's see. Then I need
we can talk about that.
I just promised because I don't just have UC but also quantum UC because it's completely generic. And that's what we're actually. So I promised to give another short talk about that tomorrow. So I have a set of slides which just have a lot of category theory on it, and I can present that tomorrow. But yeah, so it's the standard UC definitions. And yeah, so what we did was to actually check that this matches the ideal functionalities that are known there. So we get, from the game hopping proofs, we get the UC theorem, we show that it's equivalent to the ideal functionality, and then we can compose them using this UC theorem. Yeah, so this is standard and it's all proof in and then we also have the again we have the test vectors and both in Rust and Lily, so to make sure that this is actually the correct definitions. There's a whole area of research now which is called intent specification, because a lot of people work on this, and turned out that we have been using precisely these techniques, and we extended them a bit, and it actually works very well. This is what I said. So we cross-check them, the definitions. So one of the things is that we have this whole web of security definitions. So to some extent they came from EasyCrypt, and we check them with a number of sources. So EasyCrypt, SSProof, and then I looked at 4 different textbooks and made sure that they were actually all the same definitions. So this is completely standard. And we prove the equivalence, so the implications between them. So if one definition is wrong, then you would likely be unable to prove the implication. The other thing is that this helps you to actually steer the automation, because once you have sufficiently many of these protocols done, you can use them to actually I have a big collection of protocols. I can select a few of them and then give them as examples to the LLM. Here's where the definition. So here's the definition of what universal composability, and this is the part where the cryptographers really would like our help, because they're always complaining about this universal composability. So this is, we in programming language we had the Hallmark challenge, because we always have these papers in PL and with a huge appendix, and no one actually wants to read the appendix, and that's why proof assistants are very nice. So if you look at crypto, then you have a crypto paper and there's a huge UC appendix, and no one wants to either write it or read it.
And the UC paper is still being updated 20 years old.
Yeah. So we have a formulation of UC, which is a categorical formulation, and I have both a sequential and a concurrent UC, but I can talk about that more tomorrow. And so ideal functionality simulates an ideal protocol emulates an ideal functionality if there's a simulator such that the distance between the protocol where you apply the adversary and the ideal functionality applied to the simulator, this is small, and this is the distinguishing distance. So this is the usual formulation. So this is a different formulation. And we have the sequential UC and concurrent UC. This actually required a bit of work to actually get that in one other framework, but I have a solution to that. And then we have the composition theorem from UC. So if protocol P is close to the ideal functionality F, and F is close to is delta close to G, then it's transitive. So we can do transitive reasoning. And so then we get signal as a UC functionality. So signal implements the end-to-end messaging functionality. and so we get the continuous key agreement ideal functionality. So that's we prove that with the TH ratchet actually implements it. So all these steps, all these ideal functionalities, they're standard on the literature, and then you can compose these. So these are the two UC papers. So you compose these, and then you get that this actually gives you the end-to-end messaging or end-to-end channel functionality. So the bounds you get for that. Here's the components, the corresponding Lean theorem, the bounds, and what we did is also check carefully that these bounds actually corresponds to the published bounds in the papers. Before this was a source of errors, but now we actually checked it correctly, or well, in some of the other protocols, this was a source of errors. So now we actually have, for each of these security theorems, we have a very clear link to a precise lemma in the literature. And then you have the composition here.
What's the difference between triple ratchet and SPQR runs? This diagram. Oh, one's for UC and one's for okay.
This is the Rust implementation. Yeah.
Okay.
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 So that's actually I think the next slide. Yeah.
Okay.
So this is the CRISPR implementation. So then we start from, and that one is Hacspec, so we can directly translate that to link, and then prove one of the things we proved that this is actually panic free, and I think what I did was just force your proof to have star to
Yeah, for a second. The implementation is all signal very sensitive about this. We only help them do the proofs. So
okay.
Yeah.
So this is what I use here. So mostly what I wanted to try out, and so one of the questions is, do we still need all these different systems, or can we all use the same system? So can we all use Lean? And that seems to be the case, at least for this use of F-star. So to prove panic freeness, this actually works quite well just in the interaction. So that's one of the places where we don't need F-star anymore. I think I've said the rest. And then we get UC version for the actual implementation of this protocol.
What model of the Rust standard library did you use? Did you make your own?
This is an effort by CRISPR to model as much of the standard library as possible. So I use those.
Probably have to extend it a bit.
Yeah. One of the things I did, and that's online now, is to model all of the libcrux, and in the same way as I said before. And that's a big effort also by CRISPR, and also has some students working on that, trying to see if we can automatically get these hex models out of more and more of Rust libraries. So we actually have a specification for what it's supposed to do. Then what we want to do is to prove that MLCAP is actually secure, and so it's classically secure. So we did the classical reduction. There's also it's also secure in the quantum random oracle model. So I formalized that in the and also proved this one. And now what we want to do is lift this one to. I just gave you that the signal is an end-to-end channel. But for that, if we want to do it in a quantum version, then we need to have a version of quantum UC. Fortunately, that exists. That's the work by Dominique Onkel. And that has been formalized already in Isabel. So I have a version, but that's not categorical. So I made a categorical version of that. And I proved that there's a quantum UC lift. So if you have a UC, you have a classical protocol, a classical reduction in UC from one protocol to another, then it's also a lift on the quantum side. So this is secure against quantum approaches. So concretely, we know that MLChem, it emulates an ideal chem against quantum approaches with boundaries. And this is the quantum hardness assumption, is quantum module spelling with errors. So this is all standard theory, but this requires making a model of quantum mechanics, quantum channels.
Did you say that the proofs in UC hold also in quantum UC?
Yeah. That's the theory.
But so that UC can do proof by rewinding or anything like this?
Yeah. So that doesn't fit directly. That's a theorem by Dominique. Yeah.
So there's like no restriction in the UC theorem, like there's no additional hypothesis, it's like for all UC reductions?
Yeah.
Okay.
At least that's the formulation here. Okay. So there's a So I proved this UC lift theorem. Okay. And then, so to go back to Leo's talk yesterday, so we've been using the work by Anders, just to shift gears, and also Anders was asking about secure implementations. So this is so one of the things we want to do is to have efficient cryptographic primitives, and what we did, we have libraries in rock, and so we want to have efficient implementations of the primitives that Signal is using, and this is built on top of work. So this is related work we have been doing. We have been formalizing on top of fiat cryptography. Fiat cryptography is a compiler for finite field arithmetic that's used by the elliptic library. So that's already used in production by Signal. And so what we have been doing was pairing friendly curves, but also Ethereum is using in the KZG commitments. So that's something that we've done now. But for that, we need efficient implementations of the BLS curve. That's some class of elliptic curve. And that's something that we have been doing with Diego Araya, who's an expert in cryptographic implementation, one of my close colleagues, and two PhD students. And this work was actually extremely hard. So we got up to verifying scalar multiplication in the elliptic curves, and that's about as far as we could come. And then I recently wanted to finish this, so and I've now finished the full proof. And so what we have been doing is only this particular curve, which is the one. This is the one used in KCG. I think this is the one used by Ethereum at the moment.
Yeah, we have an EPS pre-compile.
Yeah.
But it was stupid to add it, so you want to assume it.
Yeah. So the way this works, again, what we started out from Hacspec, and then embed into rock, and then use fiat cryptography. So that we have the fiat compiler that gives us codes in because the portable code, so it gives you I think they have backends in C, Go, Rust, maybe also Nick. Then another part is Rusicola, which generates bedrock C. So this is a very small version of C. And we use C for the tower arithmetic. So there's a tower of field extensions, depending on what curve you use. So sometimes it's usually it's three different three or four finite field extensions. Sorry, three extensions, which means you have four fields in play. And we actually so this gives you the full constructions that you need to implement the KCG commitments with all the optimizations that actually have been informed. And we have printers, so both have been proved correct in ROC. So this is new. So we have a Jasmine bridge. So Jasmine is high-level assembly, portable assembly, and the nice thing is that it is actually constant time because cryptographic. This is fully formalized in ROC, and it's connected to EasyCrypt, where they usually use the security groups. I don't think this is no longer necessary because we could do the whole thing in Lean. But here we were in ROC, and we actually we have the compiler here, and then from bedrock C we actually generate Jasmine, and then we generate very efficient proof. So we get verified x86 assembly with verified Rust wrappers around it. And yeah, this work. So Anders has been complaining a lot, and I think that this is you gave a very nice way of solving this. I can say this is doing this was extremely painful, and to actually finish this, the proofs are long. One of the things I found recently is that we have. What I did was Bedrock has a very small language, C-like language. But we have a printer a verified printer to a Troy language of Rust. Now we have the borrow checker, and that actually makes sure that we can avoid a lot of the proofs in separation logic. And I think that that's a general. That seems to be the general consensus. So don't do C verification, but first rewrite your programs in Rust and then do the Rust verification. And I redid some of the proofs here by now, and they're about 50% shorter. And that's for the lower level. For the higher, for the more complex work, the payoff is not that big, but still you cut off something like 10%. Then we have the the nice thing is that this has all been formalized in ROC, and it's all parametric. So we have typically these things are written in assembly and very specific both for the hardware and for the particular curve. So now we can do it completely generic. So we have the whole family of curves, and the optimizations that we have for one curve can be reused for the others. This is some 40,000 lines of ROC. I started to port some of this to Lean, and I would be very excited to see if we can actually port the full library to Lean. I did a very small experiment, and that gave us I think a 40% reduction in the code, and I think if we work hard on this, that can be a lot more, both on the inside of using Rust instead of C, and all the cleverness you presented yesterday. So I think that this would be a very exciting test case because it's a huge library, and if you want a test case for the new technique, making this fast. Will actually show you that you solved all of the problem. The nice thing is that it's so the code we generate these are some of the operations. It's actually faster than some. So this is highly optimized.
Elliptic does have some verification. I think Garrod can work on it.
Yeah, but that's very limited. Yeah. But yeah, that's
there are a lot of issues with using it more than issues in it.
Yeah.
Actually.
So what they verify, I think, is the field operations. But this,
It was before my time.
yeah. But certainly not the full.
No. And there's a ton of like when people try to use BST, like using it is very safe.
Yeah.
Very unsafe.
Yeah.
Whoa. Okay.
So here what we get is So this uses a lot of cleverness, not by me. So it uses Jasmine, which has a lot of verification and extremely well designed, and it's portable. It uses something called cryptographic that Anders is also involved in, which does evolutionary search to find permutations of the assembly, and then finds a better. Just by testing, it finds a faster implementation and then outputs the proof that it's actually equivalent. So that goes into that, and then so that makes the whole thing is actually very fast. For many of these things, there's no reason why it cannot. The other thing is that this is still provably constant time, and I'm not sure that PLS is constant time. I don't think it is.
I don't think you would be concerned for these
no. But it is a concern in other places. Yeah. But yeah, so the observation here is that we can be both fully verified up to the high level mathematics and be extremely fast. And as I said, so that depends on a lot of work that's there already. And what I'm really excited about is trying to see whether we can do this, because this was painful. Whether we can do this better in Lean, and I think that should be possible. And then so other things I built because I have the connection, and again, this is something that's painful in Rock, and that can be done better in Lean, because what I connected is via cryptography together with proof, and that means that you need to divide the Rock standard library that's used in Bedrock and via cryptography with S-proof, which is based on Mathcom, and one uses type classes and the other one uses canonical structures, and then the connection doesn't work well. So that's so I have the implementation, and then we made the bridge between the SS-proof world and the cryptography world, and then actually proved these constructions here. So we have the PLS signature scheme, the actual curve. We do hashing to curve by a Rock variant of SHA-3, and this is validated as in this test vectors. And then we have we go all the way from the high level specification to low level implementation. And then we have proved all these optimizations. So the nice thing about elliptic curves is that you can get it very fast. Once you have you use things like Jasmine and Cryptops is all about algorithmics, so it's doing clever things with it. And then so we use this to connect to KZG. We also have a version of KZG in Hacspec, and we can connect it up with other zero knowledge constructions. And then, yeah, so the main point is, so we had this work and I wanted to present this as a challenge to Lean because I think it connects very nicely with the new additions to Lean. So this should actually give, so I have now most of the constructions here, with some of them proved in SS proof, the other one in the cryptography and adjustment. So we actually have a version now that we use so we can use the implementation of the curve through 519 from Jasmine, then connect it up with the higher level construction from the cryptography, which I then proved correct with respect to SS proof, and it actually gets something that's faster, but it's currently used in production by Signal, so we can actually get something that's fully verified, but faster than what we're currently using. This should speed up large group messages by a little bit, but that's the only thing. So it's not like Signals are going to run a lot faster. But the nice thing is, yeah, it's completely verified. So here's what we have, and I can tell you more about the UC story tomorrow. And then we have the primitives here, where so this is still done in Rock. We have some connections between Rock and Lean, like the Peregrine, but we do compilation. So either we should push more on that, or we should push more on translating some of these things to Lean. But yeah, very excited to see what more we can do here. And yeah, we've as you've seen that there are some parts that I know very well because published about this in the previous years, and some parts that are still new and where I really would like to work. I'm going to work with the experts on making sure that everything is correct. I've done what I could using test vectors, using Hacspec, what was it? Hex reference implementations. This net of security definitions and so on to make sure that the intent was actually correct. But yeah, so this was all generated by the LLM. So there's a lot of parts that I understand, and clearly some parts that I really like to work on more with the experts, which is the reason I'm really excited that we're all here together. There's some parts that are still open. There are some details of the precise modeling of the signal protocol. What will be very exciting is to see how Hex and Linus can work together. So as I said, so I have partially verified some of these steps of Hex in Lean already, and I think that we should just verify the whole of Hex and Lean in Hex and Linus in Lean. I think that this shows it can be done. There's a nice paper and a nice implementation of Ania, so I don't see a reason why that cannot be verified in Lean. And Ania would allow us to verify the production implementation, not just the Hex models. I have versions of there's a whole zoo of UC definitions, maybe 10 different ones. I have 3 of them. So one of the questions is how much concurrency do you allow? I have a concurrent version. There's one called JUC, which is one of the strongest or one of the most precise. That one I haven't modeled yet, but that one has been used to model parts of signal. So I have in our multi-party computation paper, that was one of the first papers where we actually formalized the UC protocol. There we did active security. I have active security using these I3s. but it's not precisely this one yet because I don't have a clear story about that. And then the quantum stuff. So I have the quantum UC. I have the reductions into the quantum random oracle model. One thing that's open and that hasn't been, as far as I know, it's just open research. A real proof in that signal is quantum secure. I know what is done that. No, I mean, not even on paper. I think it should be possible. It's just no one has done that. And I think one of the reasons no one has done that is doing UC proofs is actually already too hard for cryptographers. At least that's what my colleagues tell me. But I think the reason that it is too hard is precisely the reason that reasoning about programming languages is too hard. I mean, in a precise way, because this is a compilation. It's compiler correctness, and the cryptographers don't know that, but we do. So that still needs to be done fully in the quantum setting. I think that's it.